In today's video, we're going to discuss about a dwarf planet that often remains an outcast, but definitely doesn't deserve to, and that is Quaoar. In the icy, unexplored reaches far beyond Neptune, where sunlight is a mere glimmer, lies a realm of frozen objects and cosmic mysteries. This is the Kuiper Belt, a vast expanse populated by icy bodies, dwarf planets, and remnants from the solar system's formation. Here, a small world named Quaoar, a dwarf planet composed of ice and rock, quietly orbits the sun, taking nearly 287 Earth years to complete a single revolution. For a long time, Quaoar was just another face in the crowd of Kuiper Belt objects. But in 2023, astronomers, using sophisticated telescopes and innovative techniques, made a startling discovery. Quaoar has rings, not just any rings, but a delicate and surprisingly complex ring system. These rings shouldn't exist, at least not where they are, according to our current understanding of physics and celestial mechanics. Unlike Saturn's famous rings, which are a dazzling spectacle of ice and rock particles, easily visible even through modest telescopes, Quaoars are found far outside the Roche limit, the region where physics dictates that rings can survive due to the planet's gravitational forces preventing them from coalescing into a moon. This unexpected discovery upends our understanding of how rings form, how they are maintained and persist in the solar system, forcing scientists to re-evaluate existing models. Normally, rings are found much closer to their parent planet, tightly held in place by the planet's powerful gravity, which prevents the ring material from drifting away or clumping together. But Quaoar's rings orbit at a distance well beyond this safe zone, seemingly defying the established rules of celestial mechanics. It's as if the universe is daring us to rethink everything we thought we knew about planetary rings and the forces that govern them. Quaoar's rings are a cosmic riddle, a fascinating challenge to our fundamental assumptions about the architecture and dynamics of planetary systems. This tiny frozen world, once an obscure object in the distant Kuiper Belt, has now become a major focal point for astronomers around the globe, holding secrets that could potentially rewrite the story of how planets and their intricate ring systems are formed and evolve over billions of years. The mystery surrounding Quaoar's rings is just beginning to unfold, and it's already profoundly changing the way we perceive and understand our solar system and the universe beyond. It just goes to show that sometimes the most distant and seemingly insignificant places hold the biggest and most paradigm-shifting surprises. To grasp why Quaoar's rings are so puzzling, and why their existence challenges our understanding of planetary formation, we need to talk about the Roche limit. This concept is absolutely crucial for understanding the dynamics of celestial bodies in close proximity to one another. The Roche limit is an invisible boundary, a theoretical distance, around a planet or any celestial body with significant gravity. It defines the region where gravity's tidal forces, the differential forces exerted across an object due to gravity, are so strong they can tear apart a moon, comet, or any loosely held object that gets too close. Imagine a cosmic tug-of-war where gravity is the rope. Inside this limit, debris can't clump together to form larger bodies. Instead, it's pulled apart and spread out, ultimately forming rings. Outside it, gravity is weaker relative to the internal cohesion of the particles, so particles should merge, gently coalescing over time, and form moons. It's the perfect environment for accretion. Saturn's rings, and those of other gas giants like Jupiter, Uranus, and Neptune, all sit comfortably inside their Roche limits, a testament to this gravitational principle. The Roche limit has been a reliable rule: rings inside, moons outside, a clear and distinct separation. It's a simple, elegant explanation for the architecture of planetary systems, a cornerstone of our understanding. But Quaoar's rings don't follow this rule, presenting a significant challenge to our established models. They orbit far beyond where rings are supposed to survive, defying expectations and raising profound questions. This isn't just a minor exception, it's not a rounding error or a slight deviation, it's a direct challenge to a foundational principle of celestial mechanics, forcing us to re-evaluate our assumptions. The Roche limit was supposed to be the cosmic line, the definitive boundary between rings and moons. Quaoar's rings have crossed it, blurring the lines and demanding a new explanation. When astronomers measured Quaoar's rings, they found them orbiting more than twice as far out as the Roche limit predicts. At that distance, the ring particles should have long ago clumped together to form a moon. Yet, they remain as a distinct, stable ring. defying gravity's usual script. It's like finding a sandcastle standing tall where the tide should have washed it away. This contradiction suggests something else is at work, keeping the particles apart. The discovery sent theorists scrambling for answers. Are we missing something fundamental about how rings and moons form? Or is there a hidden force at play in the Kuiper Belt? Quaoar's rings force us to question the boundaries of our knowledge. Sometimes the universe refuses to play by our rules. Scientists, driven by an insatiable curiosity, began searching for explanations to this intriguing puzzle. They delved into the data, explored various possibilities, and considered a range of factors that might be at play. One compelling idea centers on the extreme cold that permeates the Kuiper Belt, a frigid realm far beyond Neptune. At a staggering -220 degrees Celsius, the temperature plunges to levels that defy our everyday experience. In this deep freeze, ice behaves in unexpected ways, transforming into a substance that is not only hard but also incredibly bouncy, almost like a superball. Within Quaoar's rings, bathed in this frigid environment, ring particles might bounce off each other with surprising energy. Instead of gently sticking together and gradually merging into a moon, these icy particles are locked in a perpetual state of collision and rebound, effectively preventing them from coalescing. Could this extreme cold be the secret ingredient, the crucial factor that keeps Quaoar's rings perpetually intact, defying the natural tendency to form a moon? Another compelling theory suggests that the rings are relatively young, perhaps formed from a recent collision, a cosmic smash-up that shattered a larger object. This collision could have involved the breakup of a moon or even a comet that strayed too close. If this is the case, then we're incredibly fortunate to be witnessing a fleeting moment in cosmic time, before the particles have had sufficient time to coalesce and form a larger body. These intriguing ideas highlight how the fate of a ring system can be intricately linked to the tiniest details of temperature and the fundamental properties of the materials involved. It's a humbling reminder that the universe's grandest structures can hinge on the smallest physical quirks, the subtle nuances of nature at its most fundamental level. Whether it's the grip of extreme cold, the aftermath of a recent cosmic event, or some other factor yet to be discovered, Quaoar's rings serve as a captivating cosmic experiment in progress, a natural laboratory where we can observe these processes unfold. We're incredibly fortunate to be catching the system in the very act, witnessing a dynamic process as it unfolds before our eyes. It's a chance to witness the universe rewriting the rules of planetary formation, challenging our assumptions and pushing the boundaries of our understanding. Enter Quaoar, Quaoar's tiny moon orbiting farther out than the rings. Moons can influence rings through orbital resonance, a gravitational rhythm that stirs up ring particles. Quaoar and the ring are locked in a 6-to-1 resonance. For every orbit Quaoar makes, ring particles circle Quaoar 6 times. This precise timing lets Quaoar's gravity nudge the ring, keeping its particles moving and preventing them from sticking together. The combination of extreme cold and Quaoar's gravitational stirring could explain why the ring persists. It's a cosmic balancing act. Cold keeps the particles bouncy, Quaoar keeps them agitated. The ring's survival may depend on both factors working together. Quaoar acts as a shepherd, maintaining the ring's existence. In the Kuiper Belt, even a tiny moon can play a starring role in a planetary mystery. Sometimes the smallest actors have the biggest impact. Quaoar's rings don't just break a rule, they force us to rethink how planetary systems form. The Roche limit was once a clear dividing line, but now we see it's not universal. In the cold, distant Kuiper Belt, new processes may shape rings and moons. Perhaps our rules are really just local guidelines, not cosmic laws. Quaoar's rings are like a forest thriving in a desert, proof that nature finds unexpected ways to build worlds. This discovery opens the door to finding even stranger ring systems elsewhere. Our models must evolve, and our curiosity must keep pace. Quaoar's rings remind us that every new observation can rewrite the textbooks. The universe is more creative than we imagined, and the story of how moons and rings form just got a lot more interesting. The story of Quaoar's forbidden rings is about more than icy debris. It's about the thrill of discovery. Mysteries like this are the fuel of science, pushing us to ask new questions and build better tools. Quaoar reminds us that the solar system is still full of surprises. These puzzles inspire the next generation of explorers and scientists. Every step toward solving them deepens our understanding of the cosmos and ourselves. The quest to understand Quaoar's rings will drive new missions, new telescopes, and new ideas. Let's celebrate the unknown and embrace the challenge. The universe doesn't owe us easy answers, but it rewards our curiosity. Out in the Kuiper Belt, a small world is holding on to a secret, and the pursuit of that secret is one of humanity's greatest adventures.